Right, welcome everyone to today's MITP NITheCS Seminar. We've got Mawande Lushozi. He's a collaborator of mine. We wrote papers together. He's an expert on high density QGP matter, so in this forward direction. And I think he's going to tell us about this work. So Mawande, I should say Mawande is from the University of Cape Town at the moment. He did an undergraduate here at BITS, then maths honors here at BITS, and a physics honors at GCT, master's and PhD as well, and then he did a postdoc with me at the INT in Seattle. So welcome on, and thank you so much. Take it away.
Thank you for the introduction. Yeah, so actually I'm talking about since I'm here to work a little bit further with Ismail, we discuss some work we actually did together in Seattle. And I guess this was about 2 or 3 years ago. Yeah, so let's set, let me give you a little bit of background. You will clarify what all these mean, color glass means, etc. How it squeezes into the patterns. Okay, so what I do is the thing is best described as a high energy nuclear theory. So it's nuclear. It's like nuclear physics, so that we care about the constituents of the nucleus, but we want to study the high energies. So we want to go with the so-called quarks. So everyone knows the nucleus is made of protons and neutrons. Everyone knows here also knows that the protons themselves are not elementary. Protons and neutrons are not elementary. Made up of quarks. Okay. And again, it's I'm interested in the part of the starting bottom that deals with quarks. So, and here there are some summarized coming in 6 flavors, very small masses. Everyday physics, so all the physics we used to in the everyday world is up and down. Force are sufficient in describing the nuclear physics. And so the mediator between mediators strong forces. But when you look at these in detectors or in everyday life, you will never. You have the challenge that you will never see a naked quark. Okay. They are rather shy, so they come in either in pairs, a quark, an anti-quark, or they come in threes. So far, I think that's what is coming. Some ideas and some searches over there for 4 and 5 quark space. I haven't been keeping track of that, so I don't know how far that is coming along. Okay. They carry a so-called color charge, which quark can carry a color red, blue, or green, say, which is forms kind of a 3D liquid space. And what's special about these kind of quark states that they come in, so-called mesons and barons, that they have to be neutral with color. So for a meson, you have say blue and anti-blue, giving color difference. For the rest of the baryons, a prime example of baryons being protons and neutrons, they have to come in combination red, blue, forming lines, colors. I mean, that's it's not a color you can see, but just started, the quantum number that started mistakes, but color was a useful metaphor to explain this color of this color bomb states, this color response. Okay. Yeah. So what happened? So some little thing they come in this state, but if you try to split them apart, say you try to knock with some energy, try to knock quark out of the one. What happens is it supply a lot of energy, stretch them apart, and then in order to liberate the quark, you would have put in so much energy that energy is enough to produce, so it's equal, it's enough to produce a quark anti-quark. And then instead of ending up with two separate quarks, you just end up with little mesons again. So you don't want to be separate. Yeah. But there is a way that you can get liberated, and that's by squeezing the button up, because it turns out the quarks of this phenomenon that's called asymptotic freedom. So the closer you get to them, the more they behave like free particles. They actually close, they behave as free particles. So if you heat them up enough, you produce enough medium, squeeze them up enough, it's a medium that's made up of really moving quarks and gluons, the so-called quantum plasma. Yeah.
I have a question.
Yeah.
What does heating up particles do?
Well, we basically we're dumping in a lot of energy into a small volume. Typically, energy is done by collisions or collide. And how you squeeze them, we'll show you. You need more than just like a piston or something like that. Some really advanced stuff. Squeezing. Okay. So that's it, right? So we describe this aspect of the standard problem was so-called the QCD. But in order to say you understand something about a force or interaction, as a part of that, you have to be able to determine what the phase diagram of magnetic interaction is. So we can say we understand water really well, right? Not only because we understand the quantum mechanics of it and the van der Waals force and so forth, but we also know how water behaves under different pressure and temperature conditions. So it's a phase diagram is well mapped out. I know for sure that if I heat it up enough, I heat water up enough, right? I can go from steam to water without any kind of latent heat. It goes rather smoothly. And I know there's a critical point over there, what the trigger point where you get the ice, steam, and the liquid water at the same time. So it's well known. And for water, the microscopic feature of water is the molecule, water molecule. So it's fundamental degrees of freedom. Okay. So when I am studying all these phases of water, I'm talking about what the molecules are doing. So similar to like if I imagine now I'm going to more extreme temperatures, then I will start boiling off electrons. So there will be more degrees of freedom. And I can imagine heating things up so much that I'm breaking apart nuclei and you've got a bunch of protons and neutrons going apart. And then we will be more heat and you squeeze it more, and your fundamental degrees of freedom will be the quarks and gluon, because now we'll split apart the protons and the neutrons. So now we want to ask the same question. Now that you have this QCD map at these extreme temperatures and pressures, What does the phase diagram look like? So practically, even though we have the microscopic period, QCD, it's not a very easy question to answer. It's not a point. Okay? So this is the phase diagram for QCD method. At low, but over there, if you follow with temperature and pressure, you will find in the place of temperature, put other measure, other variable is the baryon chemical potential, or equivalently the baryon density. So baryon density that measures the number of quarks you have, the net number of quarks compared to the anti-quarks. Okay. So if you have quark and anti-quark, it's zero baryon number, zero baryon density. So this is a kind of a proxy for the having a lot of doping sitting with a lot of quark matter. Okay. See that at low temperatures, you find ordinary matter. Finite baryon chemical potential. The QCD method appears as normal protons and neutrons, etc. And if you squeeze them hard enough, you get state of matter that is still being studied, which is only found at the cycles of neutron stars, but we consider that to be still a low temperature. Okay? And if you heat them up, then you can get to this quark plasma, which is pretty focused gluons. And so this part is actually well known. If you draw a line going from there to with a gradient of about yes, in this case would be a half. Up to about a gradient of a half is well known from first principles quantum thermodynamics. Okay. This calculation can be done also at zero temperature and finite baryon chemical potential, but the rest of this is really just speculation. And there's a first order phase transition over here, and the critical point. This is still speculative, and the point of QCD practitioner, one of the goals of QCD practitioner is to see if they can shed light into this region. Okay. On the theoretical part, you need to, well, that's what I'll tell you about today. You need to build models, etc. And then on the experimental front, I'll explain to you how this can be looked at. Okay. So yeah, how do we study this Color Glass? And remember now, I said, okay, we know this at zero baryon chemical potential of baryon densities. On top of the possibilities for studying is that non-zero, right, finite baryon chemical potential and finite temperatures. And to do that, we have to talk a little bit about the heavy ion collision. Okay. So we want to heat things up, and you normally do this because you need to form a medium, you need a large number of particles. You use a heavy nuclei, say gold and lead typically. So currently the two places we do that, we study heavy ion collisions. The energies I'm talking about is the RIC at the Brookhaven National Lab and the Large Hadron Collider, the CERN. And the energy, the nucleon pair at the RIC, it's over 200 GeV, and at CERN you can get up over 5 teraelectron per nucleon pair. Okay. So I'm looking at a proton and carry around half of that energy. Right? And these are collided, momentarily producing a quark gluon plasma. And now, yeah, so the detector So the beam will be along some axis like this. Right? It will be a beam of heavy ions coming along the Z direction, and I represent the detector there as schematically as a cylinder. All the particles that are produced, so the explosion here from the collision, all the produced particles will then go to the detector and the straight line. And there's an angle that you can measure with respect to the beam axis, the Z axis, and that angle can form the relative quantity called the pseudo rapidity, and the pseudo rapidity is actually related to so-called the velocity of the particles along the Z-axis, which you can express as rapidity if you want to be, use the language of special relativity. It's just the log of 1 plus the velocity in Z direction of 1 minus. Oh, sorry, it's a half. Yeah, the half is 1 minus the velocity in the Z direction. Yep. I mean, the advantage of the rapidity is that unlike velocities, relativity, the add rapidities add. Okay. And in the limit that your particle mass is much smaller than the transverse momentum, then these two definitions are actually the same. Okay, so just by measuring angles in the detector, you can learn something about the rapidity of the particles that you produce. And now you can, in your detector, separate out think about two, collision, think about two sort of regimes or regions. Mid-rapidity is when you have a rapidity of 0, or if I didn't make this clear to you. If that angle over there is 90 degrees, okay, this is going to be 0. So theta is 0. So 90 degrees corresponds to like your mid rapidity. Okay, so you separate out the mid rapidity and this forward region. Okay, if the particles that are produced your collision the mid rapidity, then automatically are be captured by our detectors. That's detectors that's we understood. The state of the art detector is of maybe 3 years ago. This is what the main thing. These kind of detectors. We're very limited in the amount of detectors that would find stuff in the far water region. So mid rapidity, basically everything that's gets registered in the detector. Okay. Well, the fourth region actually, we only in the last couple of years, like I saw like a star as data that rapidities between 2.5 and 4. I started taking data, but I actually haven't seen any. Maybe as I haven't looked, I haven't seen any publications of these kinds of measurements for a little bit forward detectors. Okay. And these interestingly, this separation also corresponds to different modes of particle production actually in a heavy ion collision. Okay, so now I'm going to talk about the types of collisions again. So here we're just counting protons in our detector. So we smash a bunch of heavy ions, and then you measure the number, we count the number of protons that are produced. Okay, these 3 experiments just differ in the amount of energy that's put in. So then you see that this low energy is at AGS, so about 5 GeV is all the protons that are dumped in the central region. Okay, so why is this? Again, there's rapidity, which is for our purposes is equivalent to the super rapidity. Everything is dumped in the central region. As you ramp up the energy SPS, with 17 GeV, then we start seeing the formation of two components. The proton, the net number of protons goes down in the central region. Yep.
How should I think of those protons? Are they just part of the original nuclei, or
No, it's just whatever you produce. Yeah, something's produced, you know. Could be or it couldn't be, but definitely particle number is definitely not concerned. Okay? So you're colliding, you start off with a certain number of protons and neutrons, and the number of particle tracks you're going to see in the detector are going to be in the region of thousands. Okay? So yeah, you definitely produce particles. But we need to try to get everything happen. Like if you run the energy of the colliding particles high enough, actually you see that in the central region, what happens is the proton number just goes down. Okay. So then what you're saying then I guess is right. So what you are seeing is it reflects something of the original protons. Okay. And now when you interpret this is that at very high energies, the nuclei actually become transparent and they pass through each other. And that's why you're dumping a low number of protons. The protons are actually over there, where you can't really beyond the acceptance of your detector. Okay, so it's a high rapidity. And yeah, and these are so-called transparent reactions. So the protons are the proxy actually for the total baryon number, which is the conserved quantity. So because neutrons are much, they don't carry charge, so they're harder to detect. We don't talk about neutrons yet, but this is what I'm talking about here really is the baryon number, transport of baryon number. So now I have an interesting interesting possibility experimentally. If I want to study again, remember I'm trying to form a covalent plasma, but I'm also trying to have it in a place where the baryon density is high. So there are two possibilities. Okay. Well, want to tell you first? Yep.
You said the baryon number is conserved by
Yes.
conserved.
So you know that's why we believe protons don't decay. Baryon number is conserved.
It's an experimental observation.
It's an experimental observation. Baryon number conservation. And you start off with a certain X number of protons and neutrons, you have to end up with the same baryon number. Now we have to produce something stuff.
But how do you measure this experimentally? I mean,
Sorry, what how do you measure
the number of protons and neutrons initially and finally.
Oh, so you know initially because you are the one who decides what PV actually collect.
Yeah, initially is okay.
Yeah, and then finally you can just go and count and measure these things. Then you detect.
also this part of the standard model? It's a symmetry of the standard model of the function. If you find deviations that can
Yeah, it's not a one word actually. It's not a one word.
Just baryon number conservation.
Yeah,
Baryon plus
that's right.
minus.
Yeah. Okay. All right. Good. And sure enough, experimentally as well the matches up. Okay. I mean, yeah. And in the theory beyond the standard model, these will have protons that indicate them. Yeah. No. So as far as we know, this is a conserved quantity. Yeah. Yeah, but what happens is then, if exactly, that's a good point because if the baryon number is going low here, then it must have gone somewhere else. So it must be in the higher rapidity region. And this, I'm going to introduce some terminology shortly. Let me just see. I was saying.
But it could also sit in neutrons in principle. So because you're only counting protons.
Yeah.
So baryon number cannot be seen in here necessarily because you're not counting.
Like you think I'm creating neutrons.
I'm asking.
Yeah. No. For other reasons, we know like the ratios, like kind of baryon production should come along with the protons that are produced.
Okay.
So yeah, so that what's actually happening is really what I'm saying. These are become transparent, right? And you get sort of a slowing down. They don't like over here. If you look at this, the detector was here, but you can imagine the peaks around somewhere here. If you kind of extrapolate this, but they don't end up with the same rapidity as that. They kind of lose some rapidity and dump energy into the central region, which is it's not harmful, but not the net baryon number. You are allowed to produce protons and antiprotons, but the total number tends actually to go down in the central region. Yeah. So yeah, my point was over here. If I'm trying to form a complementary plasma, right? At the same time, at the high baryon density, you have to study the part of the phase diagram we're talking about. Then there's actually in this diagram there's actually one case in which I'm doing this. But that's in the case where I downform the energy in the central region. Yeah. Dump it in the good rapidity. But I want to discuss like a second possibility. The protons are actually protons and all the barriers are actually hiding somewhere. And that I want to tell you that actually that region as well is also a high baryon density environment. We want to spend the rest of the talk discussing that. Okay, so this is actually what you get. Right? Initially, your nuclei look like that. They look rather far from a sphere. They look rather flat because they're moving at ultra-relativistic speeds, and so they look like pancakes. They're Lorentz contracted in the direction of motion. They then pass through each other, forming a kind of a so-called color flux tube, a hot tube between them, and which then will cool down, and the flux tube will then cool down into a little particle degrees of freedom, and you should end up detecting it by detector. Okay, and what I'll see largely in the central region, net mesons will be they'll be high in the central region, and then in the fragmentation regions, the so-called the far forward regions, there were all the baryon numbers carried actually. Right? Those are called the fragmentation regions. So this is I'm feeling inside. One of the nuclei is a projectile, the other one is a target. So this is where all the baryon numbers is. Okay.
So that we should think of that as a high concentration close to the axis.
Exactly. So that will be very good for very low end. Right? Good. And in your detector, there'll be have to be somewhere there. And up until recently, yeah, there really is very little experimental information over the time. Okay, but I want to argue that this actually provides us a second avenue. Should you put the detectors at the high enough rapidity that will close to, so you have the initial rapidity of the particles minus something, minus a little delta y. When you determine this there, you should be able to gain access to access information about the high temperature, the high baryon density medium. Okay? And I want to tell you why that is. Since we're smashing this thing apart, how will they end up getting higher than normal nuclear density? We're going to talk about baryon number. Okay. So yeah. Again, the experiment that's coming soon is so-called Ford calorimeter of Alice, and hopefully, like when we talk about here, then we test it when the detectors are in place.
Is that rapidity high enough for the photo? Because that's like 5.8. So the rapidity is another 100.
Yeah. Okay. So when we calculated this stuff, we actually found, if I'm not mistaken, we found like a rapidity of around 9 or something. yeah, like 9 for the energy to the LHC. So this would yeah, well, this would mix it somewhat. But I imagine, okay, I imagine. I don't run the LHC or no, I don't know if anyone of it. But if you can just lower the energy slightly, right? Then you could get these rapidities corresponding to the fragmentation. Okay, so this is a possibility that I'm thinking of. Good. Okay, so that's good. So now let's understand the participants better. It turns out it's for very fast moving nucleus. It's not enough to. It's actually not enough to think about it as just made up of the quarks. It's the 3 quarks and nothing else. Right? But due to actually vacuum fluctuations combined with time dilation, the more you write this up, it's actually better to think about the nucleus as being chock full of partons. Right? In fact, if you think of all your the protons and sorry, the quarks and gluons jumping into normal systems, in accordance with the Heisenberg uncertainty principle for energy and time, but you speed up, ramp up the energy of your nucleus, then when you time the energy, these fluctuations will longer live. Okay, so then you have a better chance. So colloquially speaking, you have a better chance of kind of catching them before they plop back into the vacuum. Okay, and so high energy is this nucleus, even the hadron, like just like a proton, looks like it's full of lots of stuff, full of lots of quarks and gluons. And in fact, experimentally, you can measure this kind of quark in the gluon distribution. And the distribution that drives the fastest and the most dramatically actually the gluon distribution. Right? So in high energies, there's a nuclear moving at very high speeds, look like just full of gluons. Okay, so you're best thinking of them as a dense gluonic medium. Right? And at that point, you get the rising cross sections. And then at a certain energy, then you see them leveling off. Right? If you fix the transverse momentum transfer between the two things, just fix that, wrap up the energy. For fixed transverse momentum, there will be a specific energy when you see this cross sections leveling off. That's when you saturated the nucleus with the gluons of a given apparent transverse side. And this scale, this apparent transverse side is then called the saturation scale. Okay, so, you can think of the energy as being the saturation energy, or you can think of the transverse side, so-called the QS, being governing the saturation. Anyway, that's how I'm going to talk about our fast moving nuclei. Okay. And yeah, and this saturation scale, when we have some numbers out front, we choose to distinguish between the projectile and the nucleus, and actually the number that the LHC is about 2 to 6 GeV, and at the rate the saturation scale is 1 to 2 GeV. Okay. Just an aside now, just to kind of prepare for some equations I'll write down. That's doing relativity. We do relativity. We proceed with very fast moving objects in one particular direction. It's convenient to use the so-called micro coordinate. So the time, the 3 spatial coordinates there, and you just mix them up. You basically rotate your space diagram for 45 degrees. Then you can describe things in terms of these 2 new variables. No magic here. It's just a different description of same waves. Okay. What's nice about this is that if you try to work out relativistic boosts in the Z direction, you have to find out, some vector quantity. What does it look like when you're speeding it up? then you just get an enhancement by the rapidity over here, P times the rapidity of the plus component, and the suppression of the minus component. This, yeah, I mean, we're going to discuss this details are determined that this is what you get. So enhancement of the plus, a suppression of the minus component. And also your rapidity now takes on this one. We will look at our previous definition. It's actually looks like just the P plus over P minus. P representing the momentum of a given particle. Okay, so again, dense gluonic medium. Okay. So dense gluonic medium that we have, which is our colliding nucleus. We say, okay, we need to. This wave function, the occupation number is so high that actually you can think about these as the classical version of the field index. So the classical Yang field, and also you have a small complement which also allows you to use this classical field. So the things simplify very nicely. Okay, so instead of if I'm looking at a proton flying about, actually I can just describe it as a gluonic field. So now, many things, like I said, many things in the traveling proton or traveling nucleus. I can the high, the very high rapidity parts of this proton, due to time dilation, will actually appear like static in the transverse direction. Okay? The motion in the transverse direction will be just for the time dilation. So we think of those as then the classical color charges. Classical color source, that source is then the field that you produce. Okay. And the current then that you associate with this fast moving is given by that. Okay. This delta function was telling you again that this would be highly enhanced in the plus direction, as we expect all highly boosted vectors. And there's a delta x minus, which actually causes your time coordinate to be equal to your z space coordinate. It just tells you that this object is moving at the speed of light, essentially, and it's also infinitesimal in thickness. Okay, this is my model for this pancake. And then there will be a static transverse, in the transverse plane, there will be a static distribution of color change. Right? We have a color index over there. It's just actual representation. Okay. And as one thing that's peculiar with you, that you don't see a dependence on x-plus coordinate, because in our case that takes the role of you can play the role of time actually. So it tells you that these configurations of charge associated with this collision actually just static. They pose no dynamics happening in the transfer direction. Okay, so that's it. That's how I treat that fast moving. Okay, that's how I treat the fast moving nucleus. To say. I haven't written the words down, but what I'm going to do then, if I want to study the fragmentation region, I want to study what happens to the stuff that is in the far forward regions. What I have to do is just sit on one of the nuclei. Okay, so I go to the rest frame of what I call the target nucleus, and then I will need a very different description of what the quarks are doing.
Sorry, one question.
Yeah.
Regarding this current.
Yes.
So the color index A is exposed.
Yes.
So that means this quantity is not aging.
Yes. It's that's true. Yeah.
So that means it is not a physical function.
Very good observation. Very good observation. Yes.
So then where does it come in as like?
It turns out that if you if I look at the gauge invariant quantities, right? Then the contributions of this type will be, it doesn't matter the gauge, contributions of this type will be the most in half. But I can look at the field strength tensor instead, right? And actually that, yeah. But that will be the most.
You were saying that there should be a combination where that is color neutral, right? We can measure only that one.
Hold on. Okay, so now, yeah. But the color you found it in, so what do you want to tell this over here?
Yeah, that would check the current.
Yeah, so
It is not gauge beam. That means in order to measure this, and then after.
yes. Yes.
So then, what is the significance of showing this?
Like in all, yeah, it turns out like if you move like in all gauges, except for the one that sets the plus component to 0, in all gauges, this is what will happen to the either the current or the field strength tensor. The plus component will be enhanced. Yeah, it really, if you look at you have to just go ahead and calculate the gauge invariant object, and you'll see that.
Okay, so maybe you are constructing a gauge invariant quantity. It's made out of.
Yeah, I'm choosing a particular gauge. That's okay. I can write this out in a particular gauge when I'm doing it. But it'll be, this will be enhanced in whatever the gauge I choose, except for the one pathological gauge where I choose my field so that the plot component is 0. Then you get the same physics happening, but the information is shoved in the transfer component. Yeah.
Okay, and maybe we can just.
Yes, in this sense. All right, so
maybe one.
Yes.
Is it called you use the term color glass?
Oh yeah,
Color glass and so
it's a glass in the same sense that you know. Sorry.
No dynamic.
Yeah, exactly. That makes it very slow in the two scale, the scale separation. It's a solid in one time scale as a glass, but over a long time scale, like this glass is actually flowing. So this over the time scale of measuring, right? It's just a static kind of stationary thing, but we know that actually over a long enough time scale, these things are moving about. That's where the glass symbolic part. Yeah. In any case, yeah, to start with the fragmentation region, which is basically where our participants go to where our black participants were. You know, there's Isabel, Larry, and myself. You know, we're thinking, well, it's you want to do this, then you better stay on the like near the one of the colliding participants, go in the right frame of one of the nuclei, follow the target. Okay, then you did a different description. So it's no longer so one of the nuclei is the colored glass, and for the others you need a different description. So the one that happened there is that what we do is very simple. We assume a constituent quark model for the nucleus that is addressed. Okay, so and the projectile nucleus then appears even more Lorentz contracted. Okay, and if I look at this one-dimensional picture that have highly Lorentz contracted gluon field, successively striking constituent quarks, and you know this is moving at the speed of light, so you know this gluons will do the soft interaction, so we just drag them along, and we move on to the next one and drag them along, and the net result is that you end up with your nucleus after the whole sheet has passed through, but it's a transparent interactions, and when the whole sheet has passed through, then you end up with all your constituent quarks or your nucleons, but they're now much closer to each other than they were when you started. So this is how the compression happens. And this was known since the 80s, but this is before the idea of Color Glass Condensate. We will see how we can express this compression in terms of in this kind of new language, and answer question like how much energy that is dumped. Right? If you know how much energy there is, then you can just compare with other low values and see whether the energy densities are sufficient. Energy densities and baryon densities are sufficient to actually produce deconfine electricity matter. Okay, right? So it's going to be we're going to be dealing with just 1+1 dimensions for just a simplicity proof of principle. We're going to look at how the baryons are compressed in the fragmentation region. Okay, and these are hit, and we assume. Then take three particle trajectories and just see the consequences of that model before we introduce any kind of extra complication. So you'll see that the quarks then assumed to be to weigh 300 megaelectron volts, which is 2 orders of magnitude larger than what you see on the numbers in your standard model table. And this is the model, and what justifies this model is the following. Well, maybe not justifies, but the idea of this model is the following. So we know that this so-called current valence forms, up, downs, the form the proton, the neutron, these are very light, and there are lots of interactions in the exchanging nucleon, exchanging gluons, there are quark antiquarks fluctuating into out of the vacuum, and the claim is that okay, the net effect of all of those interactions that you dress out each form, okay, you dress out in the form in a cloud of quark antiquarks and the gluons, giving them an effective rest mass of about a third of the proton. Okay. And I'm sure to say, like only rather recently, the lab actually, this constituent code model is actually not that bad actually in explaining all the hadronic masses that one observed. We studied this just using steady quarks and ordinary non-relativistic quantum mechanics. You get the masses of the hadrons and the baryons spot on actually. Yeah. And
Sorry,
yeah.
didn't get it last time. I thought that constituent quarks make up a significantly small part.
Exactly. So now the model says, okay, when the proton is sitting there, the temperature and a fast moving proton is much easier to describe because we got this color glass condensate than one that's sitting there. You want to describe it in terms of before. Right? They're doing all sorts of things, and they're exchanging quarks and gluons. But we say, okay, no. The effect, the net effect of all those interactions is to actually dress up the quarks. To dress up the quark, giving them an effective mass, right? So now you're describing this also that is a constituent quark of which carries a third of the proton mass. But not only that, we move on a step further. We say, okay, now since this is dressed up with many particles, the multicolors that actually, much like even though I know that this table is made up of little, electrons and protons which carry discrete kind of spin and so forth. Those add up together to give you like a classical, like continuous kind of angular momentum. They live in a very high dimension. If I want angular momentum of this, it lives in a very high dimensional representation of the quantum very angular momentum. So that it's essentially any effects of like quantization just disappears. This is looks classical. In the same way, we want to think of these constituent quarks as there being particles that are sitting there. With the quantum numbers of quarks, but the color charge we want to say lives in such a high dimensional representation. Color is to be considered classical. Right? By classical, would just mean this color charge would just be a vector in the color space. That you can take on arbitrary values. Yeah. Okay, so Yeah, and it's very nice. We're doing a all the talk that you do classical kind of mechanics with the twist, because classical physics with the Young-Mills fields, right? So you have over here the equivalent of the Lorentz force law, right? Of this object that's hit by a sheet of color glass, and this Q here represents this sort of color charge. Okay, and you can show that let's see, in this gauge, in some gauge you can choose where this guarantees that the minus component of the momentum actually is left unaffected by the interaction. So this is the key takeaway from this paper by Kevin and the top. Okay. But, yeah, and maybe there's a necessary with from each you can link like the transverse momentum K that this resting classical particle gets. You can link it actually to each distribution of color charge that you choose to be sitting in that color we just discussed. Okay, and then the gauge invariance, I guess, is recovered here by randomized it, and if we extract these distribution from some Gaussian distribution, we can extract these chart distribution from that, and this is the so-called MV model, the Bobble model. All that to say that you can translate these into a probability distribution, right? So you bring your sheet of color glass in there, you're going to get a certain momentum kick for your particle that is at rest, and this is the probability distribution that you get. This P bar being actually the average momentum you give a particle in the Z direction. You can show then that this can be converted into a probability distribution for the Z direction, right? We care about the one-dimensional models. Yeah, so we can end up with a distribution like that. So this just means a probability of giving a resting point, giving it a momentum pz, right? And it's like a one-dimensional probability density. So it's given by that. It's just an exponential distribution with the average momentum being this p bar. P bar also being related to the saturation momentum as we just saw. Yeah. And now, yeah, that's just for one resting particle sheet of color glass. But we want to describe a nucleus. So we're going to string these particles together. Right? For simplicity, like I said, we want to keep ourselves in one dimension. Yeah. So again, very simply, let's see what happens to a string of particles, a chain of particles with a uniformly distributed, a uniform density, and this kind of space-time diagram. I assume that multiple particles are sitting at the same point, so you hit them and you don't necessarily give them all the same momentum kick, because you sum them from some random distribution, so they spread about. So this is not this doesn't mean that you're producing more particles. They just we'll just say you're just sitting a bunch of particles all at the same point, and you hit them, and then you can give them different momentum, different probabilities. And if you actually take this together, you get a one particle density of this one. So just For those of you who may not know this, by this I mean, by this type of XP in general, we normally have an X hat, like vector X, this vector, this just means that if I want for distribution of particles, if I want a certain number of particles carrying a momentum p, and also at the space location of x, then this would I would just multiply this by d3x d3p, right? To give you like the total number of particles. Just this summarizes a kind of collective motion of particles. One is the one particle of the distribution. Okay, so we go. I'm taking 2 steps down, and I'm making it a one-dimensional one, right? So for that, it also depends on time as well. Okay, so we're going one dimension, all the way down to one dimension of momentum, and one dimension of space as the z, and in that case, it takes this one, where this side. This theta function describes the matter that is behind the sheet. Okay, so there's a sheet of color glass that's going to pass through my resting chain of particles, and this is the distribution behind. This describes the distribution ahead. There's some things you can already see over here. Yes, we need there's an additional theta function. You see that at negative times, right? At negative times, remember, I'm only looking at, I'm going to look at only z positive. Negative times, I don't care about this part. But what you see is that I just have my uniform distribution with zero momentum sitting with this kind. And this is the kind of plot you get if you want to see the action. If I integrate this, over the momentum, out, and I'm left with the density in the space that depends on time. Okay, and this is what you see. There's the sheet passes along. The sheet is located here over here. There's a compression. There's a spike in the density. It goes on till the sheet passes all the way through, and then you get an expansion again of your medium. Good. So yeah. So while again, Z of R, which is it's a standard for I'm just measuring my Z coordinate in units of R being the diameter of my nucleus, or like the length of the chain of quarks that I'm looking at. Right, but the issue I have over here. Okay, sorry. Maybe let's briefly work out one consequence of this. Right? We can work out how the variables are slowed down in models. Okay, so I can change my variables to a so-called space-time rapidity. Like I'm using ether, but it's a space-time rapidity. Right? These are the same in the limit that you make t and z large. Okay, same as the ordinary rapidity we're talking about. And if I look at my distribution at the kind of late times, they see them settling down into this kind of distribution. If I want to use the variables of rapidity density now versus the rapidity, the distribution settle down. Yeah. And now remember, I'm in the rest frame of the target. So just bear that in mind. It's not absolute rapidity, it's just it's measured from the rest frame of the target. And what you see is that as you ramp up the energy, equivalently increase this QS. This distribution of baryons start moving further and further to the right. Okay? And if I think about what this means, I'm sitting. This is a distribution with respect to the rest frame of the initial rest frame of the target. Right? So we start off with 0. Right? My rapidity is 0. I'm just sitting on the target. right? And then the resulting distribution is that. Right? So this is shifted to the right by that much. Okay. Well, how I can interpret this shift is just actually that it's the slowing down of the variance. Okay. So that I can see with increasing energy where the variance slow down. Right? And actually, yeah, if you look at this, this corresponds to this curves over here correspond blue and this light blue correspond to something you find close to the LHC energies. So the prediction then is that this looking at the peak just roughly as a standard with the rapidity of the variance, you lose about 2 to 3 units of rapidity the LHC, and the trend can be a little bit lower. So we're surprised to find that actually disagrees with other methods that we used to calculate this, even though ours was so crude, one dimensional. Okay, so now let's talk about the compression. Yeah, to work on the compression, might be fooling myself. Might think, okay, let me just sit here and look at this. I'm like, okay, this is my density. That's the factor by which it decreases the compression, and that would be naive because the matter is not moving, and the compression that I'll see would be fake because the moving matter would be Lorentz contraction. So to order to calculate the real contraction, I have to move along with the matter. Okay, so to do that, I work out what the average velocity is at a given point of the matter. But giving me this couple curves, and actually I find that the co-moving density divided by that. To divide out the distribution by a gamma factor, I found that it's enhanced by a factor of about 10 to 20 LC for nuclear matter, ordinary nuclear matter, and 5 to 10 great ordinary nuclear matter. And I mean, yeah, by all accounts, this is definitely enough to form a deconfined GCD matter. Okay, so what did I do? Okay, I used this so-called MV model and the model of Color Glass Condensate to find a distribution of a classical particle start by sheet color glass, and we have an expression for compression in terms of this the saturation scale, and equivalently the energy of the collision. Right, so the barrier has to be high enough to form a problem plasma. My preliminary answer is yes, but also maybe in another talk, it's not the only thing that's going to happen there when you hit the charge particle. For the normal Q, normal electron dynamics, if I want to hit the charge particle, sure it's going to move, but it's also going to radiate. Yeah. So the next component to add on to this is actually the accompanying the gluon radiation in this case. That will add to the energy density. But that has to be taken into the mix with energy density that you need to calculate. And obviously we can get a little bit more fancy and make our distribution on like an actual nucleus. And start talking about what the effect would be if maybe these ones went to collisions and it's some slight effect. Yeah, and yeah, that's all I have prepared for you today. Thank you very much.
Thank you very much, Mawande. Any questions? I know I should ask questions, but I'm going to go over if I have questions, if I don't know. Maybe I'll ask a warm-up question. So we use this MV model.
Yeah.
And okay, so part of the reason we were working together is you're sort of more of an expert on the color glass condensate. And how do it to use a more specific?
Yeah,
Because I remember this caused a lot of simplification, right? It's quadratic,
Yeah,
it's like this exponential, and it's sort of very simple, and you can do a lot of analytics.
yeah. I don't know, but apparently it's really kind of work, only done every month. And I know other ways of doing this, but at this kind of stage, I don't think it's like, I feel like too much simplification wouldn't like, give us, wouldn't enlighten us much. Yeah.
And then 10 to 20, I don't remember it being 10 to 20. No, I could be 10 to 20. I do that. 10 to 20 is about right. The neutron star is 2 to 3.
Yeah, we should have a look at it.
Yeah. Yeah, because what I'm wondering about is how you get closer, because this is a very simple model, but I'm wondering how you get closer to reality.
Sorry, but I'm just.
Oh, sorry, so on the
The compression.
10 to 20 times the density of normal nucleus.
It's
Very, very
hard to do starch. That's good, but we have to take I mean, I had a student do a project in this. Same, told them we've got the same equation. Said like 6 times.
Yeah.
Yeah.
No, I thought that was a number we hadn't thought.
Yeah,
Yeah,
that's
so-
that's a look at it.
Okay.
I mean, one thing I did change was the saturation in the scale. You know, yeah, the saturation scale is rapidity dependent. So I think naively, like when we did this before, we just simply took the saturation scale to the just on the nucleus itself. So because 1 GeV is something. So the calculation you have to calculate so the rapidity away from the nucleus, like on the you have to calculate the separation between the two rapidity and calculate the saturation scale. This the target.
That's how you get the high number.
Yeah, then the saturation scale goes up.
What would happen if you took the static, the nucleus that you designate the target? Yeah. And instead of using raised protons, you use the wave masses.
Yeah, I mean, things. Firstly, the numbers are going to be like the order of magnitude out or something. But just from a physical point of view, it's I couldn't sell it to anyone that like you can get like such a light thing to just be sitting, it's just sitting there. It's really massive.
You're probing sure that at our normal energy scales and so on, this if you want to assign mass to a proton, probably or a quark probably take third the proton mass. But
Yeah.
if you are probing things on the time energy scales that dynamics happen inside a nucleus,
Yeah.
they use the wave masses.
Yeah. Well, I think we would need the. Okay, I'll tell you what can be done. Right now, we said we assume this is a classical particle silicon. It's going to be done, and it has been done in a more kind of sophisticated way. And you go and you actually go solve the Dirac equation for the fermion. And what we say is the mass over here actually comes the typical kinetic energy. Also turns out to be what the quantity that I think of as just the mass over there, just actually the typical kinetic energy of the core. Okay, and then this becomes like a relevant quantity when we do the calculation level. But it's interesting in that with that simplification, then you can get away with just saying, okay, oh no, actually these are just constituent quantities. Yeah. Okay.
Also, the model holds for you can have the model holds. It doesn't have to be on the core level. model all you could do is say, okay, I have a glass of static protons and neutrons that are exchanging pions. And I have this underlying pion glass. And then I apply this to quarks and gluons, and they radiate quarks and protons and neutrons, and they radiate pions. Just different pions. And then you can use the proton mass. Pions.
So you see that's sort of a big.
Yeah.
That's right.
That is. Awesome. Well, thank you very much, Mawande. Thanks for whatever is left of the week. Tomorrow and Thursday. So if you want to chat with him or with us, we'll be working on coming up with some more pages about this. Good. Thank you, everyone. Have a good afternoon.